Hello, this is our project on a container door hinge in pin analysis. I'm Caden.
I'm Shay.
I'm Kieran.
And I'm Chris.
So the overview of our project, we will be going through our failed part, our failed scenario, assumptions, calculations, and FEA, and then finally a results comparison. So for our failed part, the analysis focuses on two key components provided by Cormac Industries, the container door hinge flap and the stainless steel bracket and bolt with an emphasis on the bolts. These hinges play a crucial role in securing and supporting shipping container doors during storage, transport, and handling. Each hinge is rated for 100 kilogram load capacity, ensuring they can bear the door's weight and withstand operational stresses. Their performance is critical to maintaining the integrity and safety of container doors throughout their life cycles. So, our failed scenario. A real-life incident report from the International Marine Contractor Association highlights the failure of container door hinges operating in harsh marine conditions. Factors such as prolonged exposure to saltwater, humidity, extreme temperature fluctuations, lack of maintenance, and high-frequency cyclical loading contributed to the failure. Corrosion, including pitting and crevice corrosion, weakened the hinge material, leading to crack formation and propagation over time. This fatigue process ultimately resulted in catastrophic hinge failure, rendering the door inoperable and disrupting container use. Luckily, nobody was injured, but it came very close to that happening.
So the first part of our solution was to figure out what our assumptions were. So for our material assumptions, we assumed that the hinge was made of uniform stainless steel with no defects. This means that the entire hinge, there's no stress concentrators anywhere that we wouldn't expect them to be, and just simplifies the overall analysis. For our manufacturing and design assumptions, we assumed that the hinge would follow the standard tolerances provided by the manufacturer. This would just mean that all three hinges would have the same design, and there wouldn't be unknown factors causing one hinge to perform differently than any other given hinge. For our loading and usage assumptions, we assumed that each hinge can support a maximum of 100 kilograms per hinge. But as we figured out a little later, the hinges will not have the loads evenly distributed across them because they are loaded vertically. So the top hinge and bottom hinges will have moments on them, while the center hinge will not. We also had variable loading conditions could be considered, but they are not the primary mode of operation, and we would mostly be designing to the average scenario of daily use, so just opening and closing the container. For our environmental assumptions, high humidity, salt exposure, and temperature ranges below 100 degrees Celsius and used daily. And our failure and testing assumptions, failures will originate from the component, not defects in test equipment, and our FEA model will accurately represent real-world conditions. And then for our mechanical and material assumptions that we used to determine our fatigue factor of safeties, we used 90% reliability. The temperature is below 450 degrees Celsius. No corrosion is present because that would greatly complicate the analysis and add in stuff that we have not learned yet. Our material is 304 stainless steel with an open tensile strength of 75,000 psi, a yield strength of 30,000 psi, a steel correction factor of negative 0.1 for calculating the cycle steel break. 40% elongation at break means it's a ductile material. Our modulus of elasticity is 28,000 KSI. Our pin diameter is 0.47 inches, and the door will be supported by 3 hinges vertically. It weighs 250 pounds, has a height of 102 inches, and a width of 48 inches, as shown in the free body diagram on the next slide.
So looking at the free body diagram on the right side is our initial thought and process and layout of like our door and our 3 hinges. So there's a 3-pin and 3-flange layout on the right side, and this was our initial free body diagram with only one distance used from the center of mass to the center of the pin. But after more analysis, we learned that for each pin and flange, that there was a distance needed from both the left end of the flange to the center of mass, and a distance from the right end, or the center of the pin, to the center of mass as well. And this is because the center of mass is what's creating the moment and bending stress, and the bending stress is being caused from the left end of the flange, not the right. So we needed both distances from the center of mass to both ends of the flange to move on with our analysis, which will be shown on the next slide. So our given values are shown on the top. So we have the weight of the door, which is equal to 250 pounds, and each pin is going to carry a third of that load, which is 83.3 pounds. And then you can see that each of the pin loads is equal to one another. We also have the diameter of the pin, which is 0.47 inches. And then using the distances on the door on the last slide, also shown on the left side as well, we calculated each of the distances shown, which are distance from the center of the mass to the left end of the flange and both the right for each of the pins. Then I moved on and calculated the eccentric moment of inertia, which is different than the moment of inertia. But we use this for both the left and right side. You use this by calculating the distance squared of each of the distances from center of mass to the ends of the flange. And then after that, I calculated the moment of inertia for the pin, which is the pi times the diameter of the pin to the 4th over 64. And then for calculating the moment of inertia, or not the moment of inertia, the max moment, we calculated the max loads, the 250 pounds over 3, which is the force on one pin, times the distance to the left end of the flange, because the left end of the flange is what's creating the bending stress. Then moving on for each of the forces in the x and y direction, we use the equation the mc over I, using the corresponding values for I. And in each of the x and y forces components, each of them are labeled with an L or an R, representing if that's for the left end of the flange or the right end of the flange. And then at the very bottom, I calculated the axial stress, which is calculated from the weight of the door on each pin, which is the 83.3 pounds, plus the 5.243 pounds to calculate the axial stress. And that 5.243 is shown on the right side, the reaction in the y direction on the right end of the flange, which is on the pin.
For our static software calculations, again, we'll note that the diameter of the pin is 0.47 inches. The ultimate tensile strength is 517.107 megapascals. Our yield strength is 205 megapascals. And again, our weight of the door or force of the door is 250 pounds. And that force will be divided by 3 because we have 3 hinges supporting this load. Moving on, we'll see that our shear stress, we'll calculate the area of the pin, and we'll use that area for our shear stress calculations, which is the 4/3 over force over area. Due to the fact that this is a round cylindrical rod, we'll get 4.416 megapascals. Moving on to bending stress, we'll do our polar moment of inertia, which is just pi times the diameter of the pin to the 4th over 64, again, for a round beam. And then we'll multiply that. Then we'll find our max moment and use our max moment times the diameter of the pin over 2, which is technically just our radius, over that polar moment of inertia. And we'll get 889.511 megapascals, which is going to be way too high, which we'll talk more about later when we do our ANSYS analysis. Going down, we'll do our axial force and axial stress, and we'll get 3.519 for that further calculation. And we'll substitute all those values into our von Mises equation, and we'll get, again, 887.79 megapascals, which is too high due to that bending stress. And when solving for our static factor of safety, we'll get 0.231 again because our von Mises stress is too high. For our fatigue loading, we will get our correction factor prime, which is going to be our ultimate tensile strength times 0.5. We'll get 258.554 megapascals. Our C load is going to be equal to 1 because we do have bending. Our C size is going to be 0.869 times the diameter of the pin raised to negative 0.097. And also note we are dividing by inches to make sure that our answer is unilist. For our surface, we'll get A surface going to be 4.51, B surface going to be negative 0.265. And this is going to be pulled from our data table where we are using machine to finish, and our answers will be in megapascals. Again, for this equation, we are dividing by megapascals, so we get a unitless answer. Our C temp is going to be 1 because our operating temperature for this part is going to be below 450 degrees Celsius. And we are aiming for 90% reliability, so we will have a C reliability of 0.897. Multiplying all these values together for a correction factor of 174.612 megapascals. We'll note that our alternating stress should be the same as our von Mises, but our von Mises is way too high. Again, so when we plug this value into our fatigue factor of safety loading, we do get 0.197, which is, again, too low for what our application. And then below that, we'll have our cycles to failure, which using the A fail, B fail ratio, we will get 10 cycles, which again is wrong due to that bending stress being so high, which we will get more into in our ANSYS analysis in just a second.
So for our initial ANSYS setup, we used 0.25 inches for the meshing. Obviously, this is an image of our bolt system and hinge and the pin, obviously, where we applied a fixed support at the bottom with cylindrical supports in those holes. We applied a force and then a bearing load to the pin itself due to some limitations with applying the force in general. And then we generated a SN curve in ANSYS to reflect the curve on the slide, which is the 304 stainless steel SN curve typically used. And then for our analysis and results in ANSYS, we found that our von Mises was actually around 9,453 psi with a shear stress of 5,141 psi, and that gives us a factor of safety for fatigue at 1.3, which is much more accurate.
So for our results comparison between our FEA analysis and our hand calculations, our FEA factor of safety was the 1.3 from the previous slide, and our hand calculation factor of safety was 0.197. So some reasons for the difference. For our hand calculation, we did only analyze the pin, while in ANSYS we had the full assembly of the pin nut and mount. Although the factor of safety that we got from the FEA was the factor of safety of the pin, some of the force may have also been absorbed by other components in the assembly that we did not analyze in the hand calculations. So the ANSYS calculations are more exact because they're able to account for other variables that may have not been considered in our hand calculations. So they're most likely much more accurate than our hand calculations. And what is probably the largest source of the difference between the FEA and hand calculation factors of safety is that there was an error in calculating the bending stress in the hand calculations, which caused the value of the bending stress to be much higher than we expected it to be, which caused the factor of safety to be much lower. We were not able to find exactly why our bending stress was that much higher than it should be. But since we double checked everything with the FEA calculations, we realized that the FEA was giving us a much more reasonable factor of safety than the hand calculations.
And to wrap everything up, we wanted to sum up our analysis. So we learned that specifically on our project, learning something that has a more complicated application, FEA tools make analyzing fatigue failures much, much easier and are very important to allowing us to work with things beyond our means and current knowledge. And FEA tools allow us to analyze situations that are way more advanced than we could do by hand. And like we said in previous slides, the hand calculations were very inaccurate. I mean, for example, only about getting 10.5 cycles is very unreasonable. But we learned that using the FEA values and the discrepancies between the hand calculations and the FEA calculations, that the FEA is a reliable source as long as it's set up correctly, and that it's important to check your work with computational software.
Thank you for watching our presentation, and here are our following sources.